operates by graphs and use a shortest path algorithm to compute the best route between 2 points. In this and many practical applications, we might want to find the shortest path from one vertex S to only one other vertex T. Currently there are no algorithms in which finding the path from S to one vertex is any faster than finding the path from S to all vertices. We will examine algorithms to solve 4 versions of this problem. First, we will consider the unweighted shortest path problem and show how to solve it in O. Next, we will show how to solve the weighted shortest path problem if we assume that there are no negative edges. The running time for this algorithm is O when implemented with reasonable data structures. If the graph has negative edges, we will provide a simple solution, which unfortunately has a poor time bound of O. Finally, we will solve the weighted problem for the special case of acyclic graphs in linear time. 9.3.1 Unweighted shortest paths. Figure 9.10 shows an unweighted graph, G using some vertex, S, which is an input parameter. We would like to find the shortest path from S to all other vertices. We are only interested in the number of edges contained on the path, so there are no weights on the edges. This is clearly a special case of the weighted shortest path problem, since we could assign all edges a weight of 1. For now, suppose we are interested only in the length of the shortest paths, not in the actual paths themselves. Keeping track of the actual paths will turn out to be a matter of simple bookkeeping. Suppose we choose S to be V. Immediately, we can tell that the shortest path from S to V is then a path of length 0. We can mark this information, obtaining the graph in figure 9.11. Now we can start looking for all vertices that are a distance 1 away from S. These can be found by looking at the vertices that are adjacent to S. If we do this, we see that V and V are one edge from S. This is shown in figure 9.12. We can now find vertices whose shortest path from S is exactly 2, by finding all the vertices adjacent to V and V, whose shortest paths are no. T. VV. VVV. VV figure 9.10 An unweighted directed graph G. VV. VVV. VV. 0. Figure 9.11 graph after marking the start node as reachable and 0 edges. VV. VVV. VV. 0. 1. 1 figure 9.12 graph after finding all vertices whose path length from S is 1. VV. VVV. VV. 0. 1. 1. 2. 2. Figure 9.13 graph after finding all vertices whose shortest path is 2. Already known, this search tells us that the shortest path to V and V is 2. Figure 9.13 shows the progress that has been made so far. Finally, we can find, by examining vertices adjacent to the recently evaluated V and V, that V and V have a shortest path of 3 edges. All vertices have now been calculated, and so figure 9.14 shows the final result of the algorithm. This strategy for searching a graph is known as breadth-first search. It operates by processing vertices in layers. The vertices closest to the start are evaluated first, and the most distant vertices are evaluated last. This is much the same as a level order traversal for trees. Given this strategy, we must translate it into code. Figure 9.15 shows the initial configuration of the table that our algorithm will use to keep track of its progress. For each vertex, we will keep track of 3 pieces of information. First, we will keep its distance from S in the entry D. Initially all vertices are unreachable except for S, whose path length is 0. The entry in P is the bookkeeping variable, which will allow us to print the actual paths. The entry known is set to true after a vertex is processed. Initially, all entries are not known, including the start vertex. When a vertex is marked known, we have VV, VVV, VV, 0, 1, 1, 2, 2, 3, 3. Figure 9.14 Final shortest paths. V known dp Vf infinity 0. Vf infinity 0 volt F 0 0. Vf infinity 0 volt F infinity 0 volt F infinity 0 volt F infinity 0. Figure 9.15 Initial configuration of table used in unweighted shortest path computation. A guarantee that no cheaper path will ever be found, and so processing for that vertex is essentially complete. The basic algorithm can be described in figure 9.16. The algorithm in figure 9.16 mimics the diagrams by declaring as known the vertices at distance d equals 0, then d equals 1, then d equals 2, and so on. and setting all the adjacent vertices W that still have D equals infinity to a distance D equals D plus 1.
Stupid
Void
bastard.
graph.
Stop trying to hurt me.
S
I'm gonna
dist equals
kick your
0.
ass when I see
For
you.
each vertex V if.
Beat the crap
Figure
out of you.
9.16
Stop trying to hurt me.
pseudocode for unweighted shortest path algorithm. V. 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 Figure 9.17a bad case for unweighted shortest path algorithm using figure 9.16. By tracing back through the p variable, the actual path can be printed. We will see how when we discuss the weighted case. The running time of the algorithm is O, because of the doubly nested for loops. An obvious inefficiency is that the outside loop continues until num vertices 1, even if all the vertices become known much earlier. Although an extra test could be made to avoid this, it does not affect the worst-case running time, as can be seen by generalizing what happens when the input is the graph in figure 9.17 with start vertex V. We can remove the inefficiency in much the same way as was done for topological sort. Equals infinity. Sum. At any point in time, there are only two types of unknown vertices that have D equals cur dist, and the rest have D equals cur dist plus 1. Because of this extra structure, it have D is very wasteful to search through the entire table to find a proper vertex. A very simple but abstract solution is to keep two boxes. Box number 1 will have the unknown equals cur dist, and box number 2 will have D equals cur dist plus 1. The test to find an vertices with D appropriate vertex V can be replaced by finding any vertex in box number 1. After updating W, we can add W to box number 2. After the outermost for loop terminates, box number 1 is empty, and box number 2 can be transferred to box number 1 for the next pass of the for loop. We can refine this idea even further by using just one queue. At the start of the pass, the queue contains only vertices of distance cur dist. When we add adjacent vertices of distance cur dist plus 1, since they unqueue at the rear, we are guaranteed that they will not be processed until after all the vertices of distance cur dist have been processed. After the last vertex at distance cur dist dequiescent is processed, the queue only contains vertices of distance cur dist plus 1, so this process perpetuates. We merely need to begin the process by placing the start node on the queue by itself. The refined algorithm is shown in figure 9.18. In the pseudocode, we have assumed that the start vertex, S, is passed as a parameter. Also, it is possible that the queue might empty prematurely, if some vertices are unreachable from the start node. In this case, a distance of infinity will be reported for these nodes, which is perfectly reasonable. Finally, the known data member is not used. Once a vertex is processed, it can never enter the queue again, so the fact that it need not be reprocessed is implicitly marked. Thus, the known data member can be discarded. Figure 9.19 shows how the values on the graph we have been using are changed during the algorithm. Using the same analysis as was performed for topological sort, we see that the running time is O, as long as adjacency lists are used. 9. 3. 2 Dijkstra's algorithm. If the graph is weighted, the problem becomes harder, but we can still use the ideas from the unweighted case. Void graph, unweighted, Q. For each vertex V dist equals infinity. S dist equals 0.
It's too much information. I mean, how's this language even going to survive the next 20,000 years?
For each vertex W adjacent to V if.
Because of what
Figure
you've done
9.18
extenuating
pseudocode for
everything
unweighted
so far.
shortest
Is that
path
what you
algorithm.
wanted?
We keep
I
all
thought
of
you
the
wanted
same
this thing to
information as
live.
before. Thus, each vertex is marked as
How
either
long
known
did
or unknown.
languages survive,
A tentative
man?
distance D is kept
Quite
for each
sad.
vertex. As before,
You got
this
6,000
distance
years
turns
on
out to be
ancient
the
Greek.
shortest path length from S to V using only known vertices as intermediates.
You really want
As
that one
before,
to stick
we
around.
record P,
Is
which
there
is the
anything
last
that can
vertex to cause a
compact
change to D.
information in a,
The
like,
general method to solve the single
smaller
source shortest
into
path
bigger
problem is known as
chunks, so you
Dijkstra's
say
algorithm.
more
This
by saying
30-year-old
less.
solution is a prime example of a greedy algorithm.
That way you wouldn't have
Greedy
to read the
algorithms
book.
generally
You just
solve a
have to,
problem
like,
in
read a
stages
couple
by
of
doing what
glyphs
appears to
and
be the
you
best
get
thing
the
at each
entire
stage.
amount
For
of
example,
information.
to make change in U.S. currency, most people
the
count out the
Egyptians had
quarters
it right.
first, then the dimes, nickels, and pennies. This greedy algorithm gives change using the minimum number of coins. The main problem with greedy algorithms is that they do not always work. The addition of a 12-cent piece breaks the coin-changing algorithm for returning 15 cents, because the answer it gives is not optimal. Dijkstra's algorithm
My name
proceeds in
is,
stages, just like the
I'm
unweighted
here to
shortest
show you
path
how to program
algorithm.
in
At each
Python.
stage, Dijkstra's algorithm selects a vertex, v, which has the smallest d among all the unknown vertices and declares that the shortest path from S to V is known. The remainder of a stage consists of updating the values of d. In the unweighted case, we set d equals d plus 1 if d equals infinity. Thus, we essentially lowered the value of d if vertex v
It's
offered
not
a
going to be
shorter
fun
path.
for you when you see
If we
me
apply the
actually
same logic
win,
to the weighted
you know.
initial state v dq'd v dq'd v dq'd v known dp known
I
dp
had to
known
dunk
dp
some
known
people,
dp
man,
vf
along
infinity
the
0
way.
f1 volt
Some of
t1
these
volt
ideas
t1
that they
volt
suggested to
vf
me
infinity 0 f infinity
are
0
just
f2
so
volt f2
terrible.
volt vf 0
You
0
know,
t
I
0
had to
0
dump
t
some
0
people
0
off,
t
you know.
0 0 VF
Now you're
infinity
not
0
coming
F
with,
infinity
no
0
sir.
F2 volt VF infinity 0 F infinity 0 F infinity 0 F infinity 0 volt F infinity 0 F1 volt T1 volt VF infinity 0 F infinity 0 F infinity 0 F infinity 0 Q VV VV V VV VV DQ V DQ V DQ V DQ'd V known DP known DP known DP known DP VT1 volt T1 volt T1 volt T1 volt VT2 volt T2 volt T2 volt T2 volt VT00 T00 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 volt F2 volt T2 volt T2 volt T2 volt VF3 volt F3 volt T3 volt T3 volt VT1 volt T1 volt T1 volt T1 volt VF infinity 0 F3 volt F3 volt T3 volt Q V VV VV empty. Figure 9.19 How the data change during the unweighted shortest path algorithm. Equals d plus cv, w if this new value for d would be an improvement case, then we should set d. Put simply, the algorithm decides whether or not it is a good idea to use v on the path to w. The original cost, d, is the cost without using v. The cost calculated above is the cheapest path using v. The graph in figure 9.20 is our example. Figure 9.21 represents the initial configuration, assuming that the start node, S, is V. The first vertex selected is V, with path length 0. This vertex is marked known. Now that V is known, some entries need to be adjusted. The vertices adjacent to V are V and V. Both these vertices get their entries adjusted, as indicated in figure 9.22. Next, V is selected and marked known. Vertices V, 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 and V are adjacent, and it turns out that